Dr. Massa, what is his specialty?
Oh, a lot of different things. I'd say like not so much like relativity, but like I would say overall physics, like cosmology, grand unified fields theories, but mainly to do with the concept of a minimal power and minimal gravitational fields. So,
yes.
Yeah, it's very interesting work. So I've been reading your stuff for a while, but I went back over it there. So apparently there was the concept of maximum power, which is, according to my notes, 3,610 to the power 59 ergs, or like erg divided by time seconds. So
you are speaking very, very quickly, very fast. I need to write. And to read, but I don't know how to read. I'm not able to read down some.
Understood.
Cavolo, come si fa qui? Wait a sec, please. A second. Wait.
Is he a professor or some or?
I think I'm actually not sure, but he's a published author. He has papers published. One with a journal that seems to have in Belgium. I think it was in Belgium. That seemed to have some connection with NASA. It said that in the footer of the paper. It had some direct connection with NASA. But yeah, his work is very interesting. I was trying to explain a bit about it. So essentially, there was the idea of maximum power, that you could have like the most amount of energy you can have released, in one go. Like it's some huge figure, but it's still a limit. And then so based off of that, he came up with the idea of a minimum amount of power.
You got frost in about a minute.
Okay. So what you heard about the maximum power. So he has an idea of minimum power. And and then so it kind of goes off from that into minimum gravitational fields. So like quantization of gravity particles. So I'm assuming that he believes the idea of a graviton, or would put stock in that concept. So his research is pretty broad. Like his equations feature terms like the age of the universe, the diameter of the visible universe. All of these things are in there. So it's pretty broad and pretty interesting.
You can ResearchGate.
It's on ResearchGate, yeah. One thing that he mentioned was RBAB. This concept of photon. But
okay. Okay. Hi. Well, what do we want to talk about?
Well, you can talk about anything you want, but obviously we brought you on to discuss your research. But you can talk about absolutely anything that's going on with you, or with your research or your research interests. Sometimes you can talk about that which is more current, up to date, but you can go back in time or forward in time, whatever.
Here I found, minimal gravitational field.
Yeah.
Ma cavolo, è sparito tutto qui.
So I need to leave earlier, cannot go
Oh,
towards the end.
oh,
Just started, Wenzong. Was that
Okay.
what you? Yeah, just I think you. So we start at 9, and yeah, so you've only just come in like 10 minutes late, and most of the time we've just been how do you say getting started, preparing, because Corrado is new to us. He's over in Italy. I'm not even sure what part of Italy. Yeah, so he's getting ready to maybe do a presentation or a bit of a talk, as much as he can do, because you know, it's a similar situation with Manuel. Like he wouldn't have the English, so we might have to communicate through translator programs, at least to some extent. So we'll see how that goes.
So how is your
Okay.
master work?
Yeah, good.
Nothing.
Okay.
I had about 4 weeks of doing a very big project, and there was 5 of us on the project. One guy never turned up, apparently some bereavement, and then 3 of them dropped out, and then the 4th guy just didn't show up at all. And then he produced, so I had to do an 80-page report in 1 week by myself, and
wow.
yeah, it was horrendous. But I got through it, and I was so.
Is that machine learning?
Yeah,
like machine learning,
data preparation, data analysis, and a couple of other things. The report writing, you know, statistics.
Okay. What do you think about?
Go ahead there, Corrado.
What do you think about the idea of minimal acceleration?
Minimal what?
Acceleration.
Oh,
Or minimal gravitational field, are the same thing for the equivalence experiments.
Yeah. So what my understanding of minimal acceleration from your work was that you could have like a minimum rate of acceleration, like a rate of acceleration that is so small that the person will not notice it, or so it could reach like,
yes,
you know, the speed of light, and they still wouldn't know they're moving. Is that correct?
This point is not clear to me.
Oh.
I don't know if the minimal acceleration is an acceleration so small that we cannot measure it, or
Yes.
or a minimal acceleration at all. There is a problem of quantum mechanics involved in this. It's connected to the concept of minimal energy. You know the minimal energy.
Yeah.
It's linked to the Heisenberg uncertainty principle, time energy.
Yes.
A finite age of the universe requires a minimal energy because we cannot have a measurement beginning before the born of the universe.
Yeah.
It's clear?
Yes.
Okay. A minimal energy suggests the existence of a minimal acceleration and a minimal gravitational field. But this is not immediately clear. We need some equation writing something, but I cannot write.
Oh, I see. You what you can do is you can share your screen with all of your papers on ResearchGate, and you can you can highlight the equations as you go. So what I'm going to do is I'm going to share my screen again, and I'm going to show you how to share your screen.
Sembra un po' assurdo sta faccenda.
So he's saying G is greater than or equal to gamma, which is the cosmological constant.
No,
right?
yeah, gamma would be the. Hang on a sec. Gravitation.
The relativistic thing, right? Is it the relativistic Einstein cosmological constant?
That appears in it, but I think that's to do with hang on, I'd have to look at it myself.
Minimal gravitational field, gamma.
That's it. Good.
Spengo tutto.
Sorry, I'll scroll up so you can read that.
Sì, adesso sono uscito qua. Questa qui la posso anche togliere.
It's a minimal gravitational field of gamma of 10 to the power minus 8 centimeters. Okay. According to this idea, every characteristic in the unit is subject to the constraint. G is greater than. In this note, I give 3 arguments supporting the idea minimal. Some possible consequences, okay, are discussed. So he say that gamma cannot go below that. There is always an acceleration. That's what he's mentioning, right? Even though it's minute.
That's interesting. You always have a very unique way of looking at things, Raja.
Yeah.
Which is good. Yeah.
I'm trying to interpret. Yeah, I mean that's what it means, I think.
Oh yeah. No, you're absolutely right. I'm just going to get rid of that because it's kind of annoying.
Ecco, questo vabbè, chiudo anche qui. Come vuoi decidere? No,
see, I would have looked at that and thought, G just can't go less than this value. Like it's always.
No, it says greater than or equal to. He's saying.
Yes, but it can't go less, right? But I just think the way you phrase that.
Like this minimal gravitational field.
Yeah, it's a more interesting kind of way of looking at it, that it's always.
Yeah. So he said it cannot drop below that. There is always a minimal thing.
Yeah. So I'll show the full text. Move to the next
that
page.
goes along with our thing also. I mean, a lot of things that we're saying.
I due schermi. Questo è per
universal law will limit the power of any source of. So he's saying that the power limit also there is a lower limit.
That's right. Yeah.
Power equal to P.
Potrebbe.
Oh, that's what he was saying. Heisenberg.
Forse se ricevo una mia email dove gli dico, senti, sentiamo un'altra volta.
This. This is your work.
Yes, I read now.
Great.
Yeah.
I gotta go.
This is an old work of mine.
Yes.
It's very years. Nel 23 May. Yes. I don't remember this one. Yes. Where is the problem? What is the problem?
Oh no. All I'm saying is, if you wanted, see, I can go back here, and I could open up like any of these files, and you can discuss any of them like at length.
See.
So, for instance, I was looking at the minimum gravitational one, which is kind of seems to be the most recent one you did, 23rd of May 2021. So that's not too long ago. Well, I mean, depends on your point of view. So I read through this one, and it discusses a minimal gravitational field, minimum power, and something about Arbab's a massive photon. Let me find it here because it might be easier.
Okay. Yes.
See, this is what you were discussing earlier, the minimum.
What's your opinion on this stuff?
Yeah, it's very interesting. It's kind of new to me, so I like the idea you have a minimum gravitational field, which you're talking about. It's also minimal acceleration, which is very makes sense because of like what is that called, Rajan, where you have the law where you're falling and it's the conservation.
Terminal velocity.
No, it's to do with, is it the hammer? You drop the hammer and the feather.
The That's a Galileo experiment.
Oh, well, not quite. From the point of view of Einstein's work, that falling into a gravitational field and moving are identical. So if you have
inertial versus non-inertial thing.
Kind of. It has a fancier name, but we know what we're talking about anyway. So if you have a minimal gravitational field, you must have this minimal motion as well, which is a very strange concept. And then if you say you have a minimal motion, then that also kind of implies a minimum amount of time, doesn't it? That things like this idea, Rajan, you were talking about as well, time is quantized, so to be like in little jump. But it doesn't have to mean that, though. You could be talking about it from another point of view, of course. And then if you quantize, how I was looking at it, if you quantize the gravitational field, then essentially you're talking about particles in the field, correct? So you believe in a graviton. Yes? Corrado.
Well, I have understood very few of what you said. For my poor English, I'm sorry. But if you write to me your criticism, I hope to answer. But I cannot speak and then I cannot understand English. I'm so sorry for this, but it's a very difficult problem. This the minimal acceleration is strictly related to the minimal gravitational field for the equivalence principle. The equivalence principle of Einstein. Do you agree on this?
Yes, that was what I was looking for. The word I was looking for was the equivalence principle.
Okay.
Yeah. Do I agree? What do you, Rajan? I mean,
there is a contention about that. There is a little bit contention. We'll talk about later, but
sure, okay.
That's okay.
But personally, right. So personally, I don't find the concept of a maximum energy, for instance, is entirely new to me. It's entirely new to me.
Maximal energy?
Yeah. So
the notion of maximal energy is entirely new to you.
Yeah.
But the notion of maximal energy, where is the concept of maximal energy?
The max power.
The maximum frequency.
The Planck energy.
3610 to the power 59 erg per second.
Maximal power?
Yes.
Maximal power?
Yes.
The speed of light to the 5 on G. Yes. 10 to the 590. 10 to the 590 erg per sec.
Yes.
Okay, this is the maximal power. Yes. But,
it's new to me. I've never heard of this before.
Yes, it's new to me.
This is a strange concept. It's good. It's good.
It's a consequence of general relativity.
Okay, yeah, I mean that makes sense. Yeah, because you have a maximum speed limit in general relativity, and you have and that kind of is this again is contentious. Like as you move, you get heavier, more massive, and then so there's like a limit on how heavy you can get or how fast you can go. But then that could be also to do with time. So yeah, okay, but I mean still a maximum amount of power sounds like the most amount of power that you can have released in the smallest amount of time, or in a small amount of time, there's a limit on this. I did not know that there could be a limit on it. This is entirely new to me.
Okay.
So,
Do you agree about the concept of minimal power?
Yeah, I think if there's a possibility of a maximum, then
yes.
Why not minimum?
A minimum, yes.
Why not? Because this is so strange, and this is even weirder.
But I think it has to do with the first law of thermodynamics, the conservation of energy. I think if there is infinite energy, or if there is zero energy, you may not have conservation of energy, probably.
Mm.
You don't think you could conserve energy at a minimal?
If it is zero, or if it is infinite, I think I don't know how you can conserve energy. Conservation of energy can occur.
Oh, that's a very good point. Again, Rajan with the great points.
This is a delicate.
Yeah, I mean, my strength is that thermodynamics was my strength when I was in school and in the college, university. Yeah. I really understood that, and I agree with that, and I want to be a thermodynamist actually, because I could really, top the level. But but the questions arise later on. Some questions arise, and now when we do our calculations, I found that I told you, I think last time, h bar omega had to be unit. So there is a maximum frequency that can have. That's about 10 to the power 26 or something, I think. Oh, yeah. 10 to the power 34. Yeah. H omega equal to 1. So it will be about 10 to the power 34. And that means that when you calculate, that's higher than gamma ray, but quasi-particle or superluminar phase can have that energy. But I'm saying that when you calculate for the temperature, it comes from the Boltzmann constant, then it comes to about 10 to the power 21 degrees or something. So I don't know whether any star can exceed that. That's like zillions and zillions, zillion times zillion or something, or billion times billion times something. So I don't know whether anything can exist. And when I looked at it, it's pretty close to what they have. It's not exactly the same, but pretty close to what they have set the maximum temperature possible in the universe. So I think it makes, I think it all comes from, finally when I thought about conservation of energy. Because how can you conserve energy? If it's infinite, then, you can take out the whole thing and then nothing happens to it. Then put it back, nothing happens to it, So where is the conservation coming from,
Yeah.
The entropy will not increase. If there is infinite energy, entropy will not, second law will not make sense. Of course, the first law has to be true for the second law to be true, So like that, thermodynamics built that way. And so entropy doesn't, so the problem is entropy doesn't increase, the time doesn't, there is no time arrow. The time arrow is because of the entropy primarily. So the time will not move in that one direction. There is no need for the time to move in that direction. And then you got time reversal problems. There is no need for the time to move on. And then the question whether life can exist, like we can exist or not, comes into picture. See, all of them get topsy-turvy because everything depends on the conservation. The conservation doesn't happen. The Carnot cycle engine, which is observable, which showed that, you cannot achieve 100%. Perpetual motion cannot occur. But perpetual motion.
Rajan, very interesting points there. Let me get in there to ask a few questions. Perpetual motion, you just mentioned there at the end. I thought perpetual motion.
You're saying something, Christopher?
Yes. I was just asking a question. You mentioned perpetual motion. Doesn't that go against the laws of thermodynamics?
It does. The Carnot cycle engine says there cannot be perpetual motion because there is only so much. It's not 100% efficient. If you look at the temperature, that says that. But I think that my feeling is at the quantum level, perpetual motion can occur. Like our PDP circuitry, almost perpetual. But yeah, it can self-accelerate.
Interesting.
Yeah, when you go to the point level, that I think perpetual motion can exist. But
oh, cool.
Then our
yeah,
go ahead.
I was going to ask, was similar to that, but basically it was a comment that you're talking about. There has to be, like, in order for things to exist, there has to be a limit set somewhere.
Yeah.
So that things can have a shape and a form. But
yeah,
I suppose, like, there could be like a higher amount of energy, but it doesn't have to be like a cap on the existenceable energy, but it could be like a hole through which, like, energy, we no longer have access to it or something. I'm just throwing stuff out there at this point.
No, that's why the vibration makes more sense, the limited sense, the time vibration, and that's why space vibration. I think you are going to work on. They meet, they form special structures which are discontinuous structure, like functors. They form like individual manifolds, which eventually can become particles. Particles and lumps like galaxies.
You see,
but also vacuum also at other places where it doesn't intersect properly, it forms. So I'm coming up with the condition that if that is above certain level, that it forms a lump, but if it is 0 or below, then it will form a vacuum or a 0 point. So I think the source and sink aspect,
Okay. Very good. So just to get back to this this paper that we were looking at. So you have Corrado, you have Arbab talking about Arbab's photon.
Cavolo, non riesco più a vedere.
Can you see?
Sorry, I can't see your faces, but I can understand your voices.
Can you see the screen with the words on it, according to Arbab 2018? A photon immersed in a gravitational field of strength G acquires mass M. Do you see that?
Wait a sec.
Yes.
Un attimo. Ecco qua. Yes, I see now.
Good.
This is my work, Mark. Well, the problem, what is the problem?
Oh, no, there's no problem. We're just discussing your work. I'm not critiquing it. I just want you to talk about it.
This is a connection with the Arbab work, here.
Yes, it's interesting because you're talking about a massive photon. The stronger the field, the gravitational field, the stronger, the more massive the photon. But
yes,
you wrote,
this is a result obtained by Arbab some years ago.
Yes, I'm trying to look at the exact sentence. Where is it written? So you say all photons in a gravitational field have mass.
Yes. This is a result of Arbab.
No, but I thought Arbab's result is that the stronger the field, the more mass of the photon, but he doesn't necessarily say that all photons have mass. Whereas I think
this is my hypothesis.
Yes.
Yes, I remember.
Cool.
And this as consequence, there is a minimal gravitational field.
Yeah. Okay, that's cool. So you also talk about Halpern and Wesson. Angular momentum is proportional to mass squared.
Yes.
Thought that was interesting. And then Peter Broch of University of Bonn, he suggested a power of 1.7 instead. So, and then you had this number. Hang on a sec. This number, 7.
7 quarts, sì. 7. Sì.
Yeah.
704, sì.
Which comes close to 1.75, which is here. Yeah. 1.75. Yes. This is. I find this interesting from the point of view of my own research, because recently I've been noticing this number 1.7 turning up a lot, especially to do with masses of particles. So, you know, I think it's kind of key. You know, it's key to the mass of the muon and different aspects. So I think it's really interesting that it appears here in terms of mass squared and angular momentum. It's more of an observation than anything else, just something that I thought was cool. So a relation connecting the rest mass of a neutrino to the intrinsic magnetic moment.
Yes.
That's coming up here, or we may have passed it. No, I think it's coming up. Or it might be in a different paper. Oh yeah, if the mass of one particle varies with time, they should all vary proportionally. This is Gruber and Graham. I think that might be a different paper. I believe it's a different paper. Hang on a sec. So,
well,
it might be one I have downloaded on my computer.
This is all the works.
This is Broch relation. That's what we were talking about already.
Many years ago. Yeah.
Sorry for scrolling through. I have to scroll to find it. Yeah, you've worked going back to 1995.
1995. Yes, I work all.
Public with NASA, some group connected with NASA. I think. Oh, so you
Minima energy investigation and radius of the universe. Yes. And what is the problem here?
Oh, there's no problem now. But I know I'm just discussing your work.
Okay.
It's interesting. So here we have a varying cosmological term cast out on all estimations of Hubble parameter H. So what I can do is I can share that. So I'm going to stop sharing this screen in order to share the other screen that I'm currently looking at. Where is it? It's not coming up. It's a shame. Okay, I can't share that for some reason, but I can read it, so I'll just continue to do that. Where's it gone? Here, no, that's not it. This is it. So we have the cosmological constant m to the power of 4. Let me think. Okay, according to a quite general argument, independent of particle physics, Gruber and Graham, if the mass of one particle varies with time, then the mass of any other particle should vary in exactly the same way. If this is true, then the mass m of the electron depends on the cosmological constant. Yes, via the law m to the power of 4 divided by the cosmological constant. It is well known that in atomic theory, the Rydberg constant or is given by 4 = 1/2 times mc squared times the fine structure constant, and is therefore proportional to the electron mass m. I don't really understand that, but the main point is that I think you're saying that basically the cosmological constant is not a constant. And the Rydberg constant is therefore also not a true constant. And neither is the Hubble constant. by that rationale. Is that correct?
Is there any constant? Anything that's constant is constant?
Oh, well, I think he's saying speed of light is constant. I think
in vacuum.
Quintessence.
Possibly, yeah. But he doesn't. He seems to be saying that C and alpha are independent of time. Alpha being the fine structure constant, of course.
Fine structure constant.
But it's to do with the fact that because the wavelength measured by one observer near the emitter atom, so near the receiver atom, the observer 2 is measuring a photon wavelength. And because of the expansion of the universe, or the Hubble expansion, that this has been spectrally shifted or something. This is trying. That's what I understand.
I don't remember the details of this work. It's an old work.
Okay.
Yeah, I'm not here the text.
Understood. This is March 8th. Of this year. But yeah, no, that's fair enough. If I could share it, I will. But I can't find it. Hang on a sec. Possibly can share it. It's just whether or not the program recognizes the application or not, and it doesn't appear to. So it is one of these. It's called Cosmological Term Neutrino Mass and Hubble Parameter. That's the name of it. So if I did I put it in here?
I repeat myself many times.
Not sure. Cosmological term neutrino mass.
Neutrino mass and Hubble parameter. 21. And see, my next work is about the neutrino mass connected to the minimal energy.
Oh, cool. That sounds interesting, because the neutrino mass, of course, is absolutely tiny, isn't it? And it's right down there. It's very close to the minimal energy, isn't it?
Yes. There is a connection between minimal energy, minimal power, and neutrino mass. I obtain a neutrino mass of about 10 to the excuse me, my pronunciation is horrible. 10 to the minus 3 electron volt. A magnetic moment of 10 to the minus 42 erg per Gauss.
Yes. Yeah,
and
I remember.
This is connected to the minimal energy.
Yeah, the neutrino work is interesting. I'm just I was listening to, we always seem to talk about her for some reason on this, Sabine Hossenfelder. I just happened to be watching a talk she was part of earlier today, and she mentioned that without a right and a left-handed neutrino particle, if they don't exist, or if the right-handed neutrino and left-handed anti-neutrino don't exist, then no particles can have mass. Or have you heard about this? Seems strange. I don't see how she came to that conclusion. There's obviously someone somewhere has proven this, but
I found that they said that they found a neutrino, the LHC.
Right.
Recently. Yeah, recently they could detect neutrino. That's what they say mentioning.
Oh yeah. So but it wasn't the issue right-handed neutrinos don't exist?
No, they didn't mention about right-handed or left-handed, but I think
because that's the issue. Neutrinos existing, yeah, okay, that's an accepted fact. The problem is that we can only find, I think it is left-handed neutrinos and right-handed anti-neutrinos, or the other way around. But they're the only ones that we can find in nature. And because of, you know, the laws of symmetry in physics, you'd expect the other ones to just be there. And the fact that they aren't is like a big problem. I can certainly see why it would be a big problem in terms of symmetry. I just don't see why how it impacts or impinges upon, you know, all particles having no mass.
Yeah, that's hard to do. But the thing is that we only know about Higgs boson that gives mass, you know, to all the Higgs field that, you know, the Higgs boson gives mass to all the particles.
Yeah.
Maybe it's connected with that. Maybe it's connected to the Higgs boson. Then it will make sense.
I think yeah, that would make sense because of course the Higgs field is really important in terms of symmetry breaking in the weak electro weak bosons.
Yes.
So maybe from that point of view, since it has such a big impact there in breaking the symmetry, maybe it also breaks the symmetry for the neutrinos. But then
maybe that's the reason. It has to do with symmetry breaking. If the left doesn't exist, if the chiral, the left thing and the right thing doesn't exist, the symmetry cannot be broken. So hence the mass, you know, it cannot acquire mass. That would make sense. If it's kind of, was she talking something like that?
No, she was, you know, the way you listen to physicists sometimes talking and they just gloss over a point that they could spend an entire show talking about. And they just, in one sentence, they just go, the neutrino, like, because we can't find these particles, we can't explain where the particles get mass from or something. So,
but here, one of the things I used, she was talking about vacuum energy density. I think that was a good talk because I could correlate, and then I will show you in our paper this thing I worked out, and I think it will give answer to a lot of questions.
Right.
You know, it's a continuation of my physics formalism, our Hamiltonian gauge that the Helmholtz, the PDP circuitry, and all that. I think it will make it a continuous and and I think I can make a statement like I said before that where is the discordance between quantum relativity and quantum and the relativity is because we have to look at the vacuum solution. Only in the vacuum they come together.
Yeah, that sounds very interesting. I'm looking forward to that.
That's what I think we can make a point in that paper. But I will show you briefly. Each person will write about 2 pages. I will show you. I have started writing. I will show you briefly after his presentation, after Corrado's presentation. But about the concept.
Rajan, we're going to finish up here then, and we'll move on to your work. One last point, 1 or 2 last final points was another paper you had, Corrado, mentioned the force of gravity changing, and I think that this is like a well-known concept, but usually they think of it as decreasing, whereas in a paper you wrote, I think it might have been the one connected with NASA, it said something about, let me see if I have this right here. Oh yeah, well, so that it is increasing effectively. The force of gravity could be increasing over long periods of time. And what the question I have for you is, what are the consequences that you foresee, out of gravity potentially increasing? I suppose aside from the obvious ones like the big crunch, does this make sense to you?
What are you speaking with me?
Yes.
You are referring to an old work by mine of 1995. Is the gravitational constant increasing? Yes, that is in astrophysical and space science. Yes. Your question, please. I don't understand your question.
What are the consequences for the universe if the force of gravity is increasing?
Yes. I don't know. I've not considered this question in my other article, my paper.
Sure. Okay. Yeah. So what did you consider? What was your what were your conclusions in the paper? I never got to the end of the paper. I don't think I did.
The end of the paper, I remember that I was thinking about the consequences of quantum gravity. And if the gravitational constant is increasing, the Planck length, the Planck mass, and so on, become very different in the past. And I remember that the conclusion was that classical gravitational theory could be true also in the very early universe. Have you understood my pronunciation?
Yeah, a little bit. So you're saying classical, like Newtonian gravitation?
No, Einstein gravitation.
Oh.
You have not my paper there with you.
Yeah, I can look it up. Hang on a sec. What was the title again?
Vado a prendere un attimo. Oh, cacchio. Allora,
Minimal energy gravitation. Oh, hang on a sec. I'll share this. Share screen. Research page. I think this is it. What I can do is I can. Oh.
143, 148. Yes.
I want to open. No. I want to do this.
Well.
So. Okay, nearly there.
This is another work. Gravitational cosmology and proton decay is another work.
Yeah.
Does the gravitational constant increase? I wrote down concluding remarks. Okay.
Yeah.
It is when I can read what. It is well known that for distances less than the Planck length, the quantum fluctuation on the metric destroyed the Lorentz-Minkowski signature of space-time. Okay? Therefore, blah, blah, blah. Therefore, it's usually believed that physically sensible considerations for very early epochs are impossible in the context of a classical non-quantum theory of gravitation. The situation would be quite different if G increases in time. An increase in G would cause the Planck length to be an increasing function of time, and the quantum fluctuation on the metric would be vanishingly small in the very early universe. Do you understand my pronunciation?
Yeah.
Therefore, thus, a fully classical description of the universe for all t is the time, would be possible. Classical, I mean non-quantum.
Yeah.
This is perhaps the most important reason to consider with interest the possibility G increasing with time. This is the end.
The derivative. Differential G.
Short and sweet.
The differential G, right?
Sì.
The differential of G.
Well, what are you saying, Rajan? You're saying the differential.
Yeah, it's a differential G dot, right? Which is different, which means that G is not constant. G dot is greater than 0 means the universal gravity is not a constant.
Yes.
Does that mean? Yeah.
Yeah, I think you're right, because it's a differential, right? It's changing, it's moving.
Yeah.
That's interesting.
So the differential.
Yeah, I like that. That's a good observation there. that I would have missed.
Thank
you. This is probably the most right. So when you were saying classical, you didn't mean Newtonian. You were talking about it's a very short sentence or a short couple of paragraphs, but it's dense.
Yeah,
isn't it?
Good.
Yeah, it is good. It's well known for like I'd nearly need like a few days to just think about it.
Makes sense. What he's saying, it makes sense. But
yeah. Okay, so you have Lorentz Minkowski signature. So yeah, I mean I can follow it in a sense. I have more of a fuzzy kind of understanding, but I believe it. I'm not saying that it's wrong or anything.
One of the things that interesting. I mean, I found that nothing is constant, like even speed. Then your idea of the fact that infinite, energy may not violate the first law may come to picture, because if you are saying it's in a bubble, it's existing, right, within a infinite system. So it can leak into that. If it is leaking into that, then nothing will be constant, really. If it is totally conserved, then something has to be constant. But if everything is changing, even alpha is changing, G is the universal gravitation constant is changing. Nothing really is constant with time or space, which means that it is leaking into that infinite system. So there is an infinite system that giving the buffer, and inside that this bubble is occurring. The universe that we live in, observable universe, is a bubble inside that, and that bubble, it can leak energy back and forth through the interface between that bubble and yeah.
I think that's kind of what I was getting at earlier, because I mean, like the idea of putting limitations on something so that so that something could come into existence, and I think that's an old kind of concept as well. Like it's a concept that's in a lot of ancient religions, and so for that reason it would ordinarily be kind of overlooked by science, or well, not dismissed, but just not counted, because it's one of those things that can't be tested, or it seems.
I also go ahead.
But of course
I also believed in an unbounded universe. I also believed in an unbounded universe.
These maximum and minimal energy. Within the framework of that mathematics is the shape of the door, into the entrance. Like if our reality is defined by the limitations of these equations that these equations bring forth, then it may also create like an infinite or finite shaped hole in the infinite, by which you sort of feel like the infinite.
Like a manifold, like a space-time manifold type thing.
Okay, so Corrado, thanks very much. Thanks for explaining all of those things to us. I know the language barrier it makes it difficult, but we understood you, and also
it was great. Thank you.
Yeah, and stick around for Rajan's presentation if you can. If it's not too late where you are. Where are you in Italy? What part? Verona?
I live in Reggio Emilia. It's a town in North Italy.
What's it called?
I repeat. Yes, I live in North Italy, in a town called Reggio Emilia. Reggio Emilia.
Reggio Emilia.
Sì, kind of. My address is in all my papers. There is my address, the name of the city.
Okay.